This is question 3 from the OCR Depth in Physics paper. It's about a swimmer being lifted by the winch of a helicopter. So this is her attached to a cable here. We're given some information about the swimmer. She's got a mass of 65 kilograms, giving her a weight of 640 newtons. She's being lifted vertically upwards, and the cable's got negligible mass. The tension in the cable is T, and that varies during the time that she's ascending. Let's just zoom that in a bit. So from T is 0 to T equals 1.5 seconds, the tension is 670 newtons, and at 1.5 seconds the tension reduces to and remains constant at 640 newtons. As we're reading that, we should be remembering that she's got a weight of 640 newtons. So immediately we can say that tell that the tension is bigger for the first 1.5 seconds than the weight, and then it equals the weight after that. The first question requires us to use Newton's laws of motion to describe qualitatively the motion of the swimmer for the first 4 seconds of her ascent. So qualitatively means we don't need to give any values here. We don't need to do any calculations. We don't need to do calculations. We don't need to give values. We just need to describe what's going on in words. So, as I said, its tension is 670, whereas her weight is 640 for t equals 0 to 1.5 seconds. We're going to write that down firstly for t equals 0 to t equals 1.5 seconds. This is the first section, or first segment of 4 seconds. There is a resultant force. The resultant force is 670 minus 640, so we put in there that it's 30 newtons. And because there's a resultant force, that means, and it's constant as well, we should say it's constant, or a better way to write that would be there is a constant resultant force. That leads to a constant acceleration. So her motion is constant acceleration. That follows from F equals ma, the case of Newton's second law where the mass remains constant. So that's the first thing. Second thing is, after that, the tension reduces to 640 newtons and remains constant at 640 newtons. That's equal to the weight. So for t is equal to 1.5 seconds to t equals 4 seconds, there is no resultant force, therefore constant velocity. Now we need to do some calculations for A part 2. Show that at t equals 4 seconds her height above the water is more than 2 meters and that she is rising at about 0.7 meters per second. So we have to bear in mind that there's two aspects to the motion. There's constant acceleration and then there's constant velocity. Both of those are going to contribute to the height, and then we'll use just the first section to work out what the final velocity is after she's accelerated. Let's start off by working out the speed with which she's rising in the second section. So we're going to use a SUVAC problem here, or it is a SUVAC problem. We're going to use an equation of constant acceleration. We'll assume she's starting at 0 meters per second. And the v is what we want to find. The acceleration, we need to work that out from F over m. And the t is, she's accelerating for 1.5 seconds. 1.5. So let's work out the acceleration. It's the resultant force divided by the mass. I've already noted above that the resultant force was 30 newtons. So that's 30 over 65, which gives us 0.4615. I'll write that down to 4SF because that's a step in my calculation. Now we can use V equals U plus AT. The velocity, initial velocity was 0, so that's just a case of putting the values in here. Multiplied by 1.5, and V then will equal, I'm just using the value that's in my calculator for the acceleration, gives me 0.69 meters per second. So we can write that in there, 0.69. So that is about 0.7. So to 2SF you have 0.69. Now we're going to work out the height that she's risen to at 4 seconds. So we've got two components to that. We've got the component for when she's accelerating. This one is for when she's at constant velocity. Let's work out part 1. We can use the data that we've already got for that. So for 1.5 seconds, 0.4615, U is 0. We use S equals UT plus a half AT squared. So we don't know that. Part 1. Right. Let's put these values in. This is 0 plus 0.5 times 0.4615. Scroll up a bit. Multiplied by 1.5 squared. That gives us, if we call this S1, so it's the first part of the height, that's 0.5192 meters. And then for part 2, we're using S equals UT, or S equals VT, I suppose, in this case. So S2 is equal to the speed that she's going after 1.5 seconds, and that is 0.69. If I just add in some more decimal places, multiplied by the time, which is 4 minus 1.5, which equals 2.5. That's 1.730. Let's add that on to, let's add these two values here. 0.5192. You can see that it's going to be over 2 meters. H is equal to S1 plus S2. That is 2.25 meters. 2.5, shall I leave it as 2.25? 2.25 or 2.3. Actually, I will make that 2.3 so that I've been consistent with my SF there. Next part. The cable is attached to a winch which is operated by an electric motor in a rescue helicopter. The supply has an EMF of 28 volts. The circuit has a resistance of 0.11 ohms and the swimmer is rising at 0.70 meters per second. So I think they want us to use that value for the rest of this question. The motor draws a current of 30 amps from the supply. We're going to calculate the power lost in the electrical circuit. So to do that, we're going to use the resistance of the circuit and the current that is flowing. So power is equal to I squared times R. So that's 30 squared multiplied by 0.11. And when we do that, we get 99 watts. That's the power lost in the electrical circuit. Notice we're talking about power lost here. It's going to be important for this question, where we need to calculate the efficiency of the motor. So let's think about what we've got here. We know that the supply has an EMF of 28 volts and it's supplying a current of 30 amps. So we can work out the power input to the whole situation from that. Power is current times the voltage. But that's the power input to the circuit. It's not the power input to the motor. Because we're asked to calculate the efficiency of the motor, we're going to have to work out what the power input to the motor is by deducting the 99 watts from that. Then we'll need to use the fact that she's going at 0.7 meters per second to work out the mechanical power that's being put into lifting her up. So we'll use power is equal to the force multiplied by the speed that she's moving. P equals FV, that will tell us the mechanical power to her. That's the useful output. So we've got then the input and the useful output. Then we can use the equation. Efficiency is the useful output over the input multiplied by 100. So let's work out the input to the circuit. We'll call it power input IC, power input to the circuit. That's going to be current times the voltage, which is 30 multiplied by 28. That's 840 watts. Next, we want to work out the power input to the motor, so I'll call that PIM. That is the power input to the circuit minus the power lost in the circuit, so I'll call it LC, which is 840 minus 99, and that gives us 741 watts. So that's the power input to the motor. Then the mechanical power is going to be the power to the swimmer. We'll just call that PS. So that's force multiplied by the speed that she's going at. Now, because she's going at constant speed, the force supplied by the winch is equal to her weight. That's 640. Back up here. Her weight is 640. Yeah. So 640 multiplied by the speed that she's going at, which is 0.7, and so we get this one. The power to the swimmer is 640 multiplied by 0.7. That gives us 448 watts. Now we can use the efficiency equation to work out the efficiency of the motor. The useful output is 448. The input is 741. Multiply that by 100. So now we get divided by 741. 60.45%. So we can write that as 60%. And that is question 3. Yep. So everything in question 3, 60% is the answer. So just quickly recap that. We need to know the useful output from the motor, the input to the motor. The input to the motor was the input to the circuit minus the power that's lost in the circuit, that's 741. The mechanical power was the useful output of the motor. That's how much power we needed to keep her moving at 0.7 meters per second. So we multiply that by the force, which is equal to her weight. That gives us 448. So, and then that's my useful output, that's my input. Put those into the efficiency equation, and that gives me an efficiency of 60%. Further questions will be coming.